So now let's talk about another base. So this is the base 16, or hexa, which is 6, and deci, which is we know is 10. So base 16 numbers. So these have a base of 16. And we'll call them hexadecimal numbers, and for short we'll just say hex numbers. But we're really indicating hexadecimal. So hexadecimal numbers go from, well, 0 to 15. Right, so our decimal equivalent, each hexadecimal digit goes from 0 to 16. So we have, right, the 16th to the 0th power, or the ones place, the 16 to the ones place, the 16th place, 16 to the twos place, 256th place, and so forth. So each digit goes from 0 to 15. And we notice that, well, once we get to 9, 0 through 9, we can just use decimal numbers to indicate those values. But after that, we start going into 2 digits in our decimal numbers, so 10, and we really want 1 digit to represent that value. And so after 9, we start with A, so A is equivalent to 10, B is equivalent to 11, C is equivalent to 12, and so forth until we get to F. So now after 9, we have A through F for our hex digits. And we'll notice that the binary equivalent for these hex digits actually can use 4 bits. So in binary, we go from 0, 0, 0, 0. To get to 15, we go to 1, 1, 1, 1. And so a single hex digit can represent 4 bits, or 4 binary digits. So we use hex numbers for 2 things: representing numbers in base 16 and as a shorthand for binary. And this one is the one we use mostly. This is the main reason we use hex numbers. This is a shorthand for binary. Writing out a bunch of ones and zeros can be kind of annoying, especially if we start getting to large bit widths. So for example, 32 bits is what our computer uses, or 64 bits. And that's going to start to be annoying. We're just going to see this like mass of ones and zeros. So instead we use hexadecimal as a shorthand for binary. And let's show how that's done. So we can convert hexadecimal numbers to both binary and decimal. So let's start by converting hex 4AF. Again, this is base 16 to binary. So we can write that, and it's most commonly written with a prefix 0x. And that 0x is not an OX, it's the number 0 and X. Okay, so we'll take hex 4AF and convert it to binary. We take each of the digits, so F, A, and 4, and write them in their binary equivalent. So 4 is, well, here's the binary equivalent of that, 4. A is, let's see, 9 we could represent, but A is the first number we can't represent with a single digit in decimal, so it's 10, 1, 0, 1, 0, so 8 plus 2, and F is 15. So 15 is all ones. And there is our binary representation of that hexadecimal number. So that's actually quite easy to convert from hex to binary and vice versa. Now we want to convert from hexadecimal to decimal. So for AF, we have a weight of 16 to the 0, 16 to the 1, and 16 to the 2, or the ones place, the 16s place, and the 256's place. So we get 4 times 16 to the 2, or 256, plus A times 16 to the 1, plus F times 16 to the 0. Or in other words, 4 times 256 plus 10 times 16 plus F is 15 times 1. And we add those all together, and we get 1,199 in decimal in base 10. So it's hard to write subscripts in text files, and so many programming languages use prefixes. So for example, 0x, like we talked about, is an easy thing to type. This base 16 is hard to type, especially in a program, for example, in a C or Java program. And we can prefix binary numbers with 0b. Again, this is the number 0, not the letter O. So 0b 1101 is the same as 1101 base 2. And you can use whichever whichever version you want, the base 2, in written assignments and exams. But so this is the most common way to write a hex number, and binary numbers can be written with that prefix 0b. We refer to groups of bits as certain quantities. So the most common quantity is the byte, or 8 bits of data, or 8 bits of information. Here's a byte over here, a byte of information. And with 8 bits, we can represent one of, well, 2 to the 8 different values, or in other words, 256 values. And the range is from all zeros to all ones, which is 0 to almost 256, but one less than that, 0 to 255. Right, just like with 2 decimal numbers, we can represent, well, 100 different values from 0 to, well, the largest value is 99. Right, our range is from 0 to 99. 0 is a value, and then 1 to 99 are other 99 values. And the other quantity that we can use is a nibble. We actually don't use this term too much, but it's kind of cute. And it refers to 4 bits of information. So we can represent one of 2 to the 4, or in other words, 16 values. And the range is 0 to, well, almost 16, but one less than that, 2 to the 4 minus 1, or 15. And so remember in our, right, so if we have a nibble of information, the weights are still 2 to the 0, 1, 2 to the 1, 2, 2 to the 2, 4, 2 to the 3, 8. So the weights of our numbers go from 1, 2, 4, and 8 for a nibble, but if we fill those all with ones, we add those all together, 8 plus 4 plus 2 plus 1, and we're going to get 15. So here's a byte of information, and half of that, or just 4 bits, is our nibble. So a byte consists of 2 nibbles. So one binary digit is 1 bit, one hex digit is 4 bits. Remember, hex is short for hexadecimal. And so if we were to write this byte in hexadecimal, we group by 4, starting from the right. Well, if it's divisible by 4, it doesn't actually matter. The number of bits is divisible by 4. So that right nibble would be 6, and the left nibble would be 9. So to write this byte of information in hexadecimal, it would be hex 96. So one hex digit is 4 bits, or 1 nibble, and 2 hex digits make up 1 byte. So just like in decimal numbers, our most significant value is on the left and least significant is on the right. So for example, here's our least significant bit, right? Its weight is 1. It has the least significance on the value of the number. And right, 1, 2, 4, 8, 16, 32, 64, and our most significant or highest weighted bit is this leftmost bit, just like in decimal numbers, right? If we draw some number 5,263, our most significant digit is on the left and our least significant digit is on the right. And so, for example, there's our least significant bit, most significant bit, least significant byte, and most significant byte, or MSB. Usually capitalize it for bytes and lowercase for bits. But there's some inconsistency there in the literature. Okay, so we have our LSB, least significant byte, MSB, most significant byte, lowercase LSB, least significant bit, and MSB, most significant bit. And we can have, even larger powers of 2, not just, using 8, groups of 8. We can have 10 bits of information, or if we have something that's 2 to the 10, we have a kilo, whatever that is. If we have 2 to the 10 bytes, we'll have a kilobyte of data. 2 to the 20 is mega, 2 to the 30 is giga, 2 to the 40 tera, 2 to the 50 peta, and 2 to the 60 exa. And so we use these terms, even though it's not quite right. 2 to the 10 is, well, we know what 2 to the 10 is. It's 1024. It's pretty close to 1,000. And so we kind of overload that term, kilo, to indicate close to 1,000, but really it's 1024. So if we get a kilobyte of data, then it's actually 1024 bytes. And so getting a pretty good deal, right? When you're buying memory and you get 10 gigabytes of data or something, or of memory, you're actually getting a little bit more than 10 to the 9. So we're kind of overloading these terms, these kilo, mega, and giga, and tera, but really they're powers of 2, but they're close to these powers of 10. So what is the value 2 to the 24? Well, we factor out the largest kind of 10 power, so in this case 2 to the 20, and then we factor out the remaining amount, 2 to the 4. We get 2 to the 24 is equal to 2 to the 4 times 2 to the 20. 2 to the 4 is 16, and 2 to the 20 is a mega, or a million, so it's approximately 16 million. And another example, how large of a value can a 32-bit integer variable represent? Well, we use 32-bit integers in programming all the time. Well, the largest value you can represent is 2 to the 32 minus 1. Well, 2 to the 32, let's factor out the largest kind of 10 power, is 2 to the 30. And we are left with 2 to the 2. So 2 to the 30 is a giga, or a billion. So we can approximately represent 4 billion with a 32-bit integer.